Okay, in this video, we get to the heart of duality. Duality is a powerful concept whenever you're doing optimization. Um, and it's got a really nice kind of interpretation or some nice usefulness when you're dealing with linear programs in specific, though it's a concept that holds true for other forms of optimization as well. And it's the idea that for every linear problem, linear program that you have, there's an associated dual optimization problem that is kind of complementary to it. Okay. And there's nice kind of properties between the solutions to the original problem, which we'll call the primal linear program, and the dual linear program. And there's ways to sort of switch back and forth between them. And there's sometimes where solving the dual is more efficient than solving the primal. And so it gives you sort of a choice on how you're going to go about solving a linear program. And that choice kind of gives you some advantages depending on how you choose. So if we've got a maximization problem in standard form, it looks like this. And rewinding and looking back at our fundamental insight, we saw that our final tableau, or our tableau after pivoting, and let's say maybe we've pivoted it and we've kept pivoting until we reached an optimal solution, looks like this. And then we said, well, this is an optimal solution if all the values in the objective row are greater than or equal to 0. So it means this is greater than or equal to 0, and this is greater than or equal to 0. These values underneath the slack variables, we called those the dual variables, which we, in the previous video, talked about their interpretation as shadow prices. And so those need to be greater than or equal to 0. And then this needs to be greater than or equal to 0. And kind of substituting in what CB transpose B inverse is, it gets us something that looks like this. And so if we actually add C transpose over to the other side, this is essentially going to be the constraints for what we'll call our dual problem. So here is how we define our dual problem. Whereas the primal problem is a maximization problem, the associated dual will be a minimization problem. What was the right-hand side here is now going to be the coefficients of that objective function. And so this was the old right-hand side is now the objective coefficients. Okay. And then the new right-hand side, or the new right-hand side was the old objective coefficients. And so, or maybe a way to say that is the old objective coefficients is now the right-hand side. Okay, and so those swap places. You'll notice now our variables y, y are the variables, are multiplying on the left. And so it's, in essence, you've sort of transposed that A matrix when you're thinking about it. And so the dual problem has a transposed matrix. Okay, the other thing to note is that here, in the maximization in standard form, you've got less than or equal to constraints. In the dual program, they're greater than or equal to constraints. Okay, and then you've got that each of your dual variables should be greater than or equal to 0. Okay, and this works the other way as well. If you've got a minimization problem in standard form, you can define its dual to be this. Okay, and so if this is your minimization problem, it will become dual here, and we make the same observations there. The difference here is that we've got a minimization with greater than or equal to constraints goes to its dual being a maximization problem with less than or equal to constraints. Okay, so key idea. I'll say primal variables So variables in your original problem are connected to, or yeah, there's a one-to-one correspondence with the constraints in your dual problem. Okay, and then primal constraints have a one-to-one connection with dual variables, meaning that for each primal variable, there's a corresponding dual constraint, and for each dual constraint, there's a corresponding primal variable. For each primal constraint, there's a corresponding dual variable, and for each dual variable, there's a corresponding primal constraint. We saw that already with shadow prices. Those were our dual variables, and each shadow price corresponded to one of the constraints. Okay, and so yeah, kind of variables to constraints as you switch from dual to primal or primal to dual. Okay. So here's a nice table. Your book has this kind of naming criteria of sensible, odd, bizarre. So I sort of wrote these out assuming that we've got everything in standard form, but that's not always the case. And so in your primal, if you're maximizing, then you're minimizing. Yeah, we've called this W for the objective for the dual problem. Then each constraint corresponds to a dual variable. And if you've got a constraint with a less than or equal to the right-hand side, then it's going to correspond to a greater than or equal to a non-negative variable. Okay. Equality constraints correspond to unconstrained variables, and then greater than or equal to constraints, which are pretty rare when you're talking about maximization. And so that's why your book labels them as bizarre choice. Those correspond to non-positive dual variables, which is kind of weird to see, but we also talked about that in a previous video on how we can deal with non-positive variables. Similarly, for each variable there in the primal problem, there's a corresponding constraint in the dual. And if that variable has the standard non-negativity to it, then it corresponds to a dual constraint with a greater than or equal to form. If the primal variable is unconstrained, it corresponds to an inequality constraint in the dual. And if it's a non-positive primal variable, it corresponds to a less than or equal to constraint in the dual with minimization. Now, I will say I labeled these primal and dual, but you could just as well label them dual and primal if your primal problem is a minimization. So it sort of goes either way in this table. So really, if your original problem is a maximization, go from here to here. If your original problem is a minimization, go from here to here. Okay, and this action of switching your problems by taking the dual is what we call in math an involution, which is a fancy way to say that the dual of the dual is the primal. So if you take the dual and then take the dual of that resulting problem, you get back to the original problem. And so, yeah, that's maybe why they're called duality, is that there's this relationship between the two. Okay. Let's see an example of this in work, because otherwise it's pretty abstract as it is there. So let's get practice writing the dual of a problem. Okay, so here we've got X variables. Notice we've got a minimization problem. So that's important to take note of. So we're going to start in the right side of this, and we're going to be essentially moving this way. Okay. And we've got 4 primal variables. And so maybe let me just make a note here. So primal, we've got 4 variables. Those 4 variables in the dual will correspond to 4 constraints. Okay, and then here we've got 2 constraints for our primal problem. which will correspond to two variables in the dual problem. Okay, so constraints to variables, variables to constraints. Okay, and let's, so those two variables we're going to call y1 and y2. Okay, so let's go about this. If we wanted to, this is standard form for a minimization problem. So we'd be looking at sort of this pairing here. But yeah, let's start off with the objective, the new objective. So now we're gonna write out our dual problem. The original problem was a minimization problem, so the dual is always going to be the opposite. So this is going to be a maximization problem. We're going to have our right-hand side. So we'll actually label maybe the objective of the primal problem. We'll call that Z. We'll call the objective of the dual problem W. And that W is going to be equal to Y transpose B. And so that y vector is going to be the vector that comes from y1, y2. Okay, and kind of I use a T for transpose to denote that this is a row vector, and that's going to multiply by what was the original right-hand side of -4, 38. Okay, so that's our new objective row. And if you write that out, that's y1 times -4 or -4 y1 plus y2 times 38. So 38 y2. Okay, and so really that is just going to be a number once we know what y1 and y2 are. Now let's look at our constraints. So then we'll say ST stands for such that or so that. And we want to have that y transpose times the A is going to be less than or equal to RC transpose. Okay, so let's think about what that looks like. Y transpose is y1, y2. The A matrix is going to be this matrix up here. And so that's going to be 1, 2, 3, 4, 5, 6, 7, 8. You can tell I wasn't having much creativity when I put this problem together. So that's that. And that's going to be less than or equal to what was the previous cost vector or objective vector up here. And so that's going to be greater than or equal to 91, 51, 7, 13. Okay, so here's our objective, here's our constraints. Now, this is actually a perfectly fine way to write out the constraints, but maybe let's actually do this matrix multiplication and think about what each of those constraints are and sort of write each of them out. So for this first value of 91 on the right side, that will be y1 times 1 plus y2 times 5. And so y1 plus 5y2 is less than or equal to 91. That's going to be one of the constraints. Then we'll take this times this, and so 2y1 plus 6y2 is less than or equal to the second entry here of 51. And then we take it times the third column, and so we get 3y1 plus 7y2 is less than or equal to 7. And then we do it times the fourth column, and we get 4y1 plus 8y2 is less than or equal to 13. Okay, and so those are our new constraints. If we kind of write them out as inequalities instead of as a matrix of inequalities. And then you could think of, okay, well, if I wrote this maybe in the normal way of writing constraints, what would this look like? Well, it would look like the matrix 1, 5, 2, 6, 3, 7, 4, 8 times the vector 1, of y1, y2, and that has to be less than or equal to the vector of 91, 51, 7, 13. Okay, and this matrix here, if we compare this matrix to this matrix that we had before, this is what's called the transpose, where we essentially swap the rows and the columns. And so to kind of do a flip-flop there. And so this is going to be actually A transpose times Y is less than or equal to, well, we called this vector up here that we started off with, or this one here, that was the C transpose vector. And if we transpose that, the result we'll just call the C vector. Okay, and so that's maybe a vector, that's a vector, if you want to kind of denote those as vectors. And so your constraints in the dual problem essentially have the transposed A matrix going with what was the previous objective vector. Okay, and so that's how we form a dual problem from a primal problem. The main thing to note is that we swapped variables to constraints and constraints to variables. And so each of these constraints, we can actually label them as this one. That all came from the x1 variable in the original problem, in that the 1 and 5 that we've got here were exactly what was multiplying by x1 in these constraints. Okay, this second constraint, that corresponds to the original variable x2, x3, and x4. So each of these constraints in the dual problem correspond to a primal variable. And then each of these dual variables, y1 and y2, correspond to a primal constraint, a constraint in the original problem. You can kind of think of, okay, this first constraint, that corresponds to y1, and the second constraint here, that's the one that corresponds to y2. y1 would be the shadow price for the first constraint, and y2 would be the shadow price for the second constraint. You can kind of also maybe think of x1, 2, 3, 4. Those are the shadow prices for the dual problem. So the original problem, or the original variables, are the shadow prices to the dual problem. Okay. One of the sections in your book, or actually the supplement to chapter 4, talks you through an economic interpretation of the dual problem. I encourage you to read that. There's some times where the dual problem has a very nice interpretation to it. So that's it for this video. Next video, we'll introduce the idea of complementariness.